In this tutorial, we shall look at electron spin and Pauli principle. In addition to N, L, and ML, a fourth quantum number was necessary to account for the details of emission spectra of atoms. The spectral data indicate that the electron has a magnetic moment with two possible orientations when the atom is placed in a magnetic field. So in this case, N, that is the principal quantum number, L, the angular momentum quantum number, and ML is the magnetic quantum number. So far we have looked at the three quantum numbers. So now we are going to look at the fourth quantum number. So the electron has a magnetic moment, which has two possible orientations when placed in an external magnetic field. It has two possible orientations. So the new quantum number that was adopted is called electron spin quantum number. Electron spin quantum number, which is abbreviated as MS. The electron spin quantum number can have only one of two values. That is positive half and negative half. So these are the two possible values that the electron spin quantum number can have. So we can interpret to mean that the electron can spin in one of two possible directions. So the electron can spin in one of two opposite directions. So here simply we can take it to mean like a coin. When you toss a coin, it can either give a head or a tail. So the electron can spin in one or two opposite directions. So it can be a spin up or a spin down. So these studies were connected to the postulate of the Australian physicist Pauli, who stated that in a given atom, in a given atom, no two electrons, can have the same set. Can have the same set of 4 quantum numbers, So the 4 quantum numbers, that is N, L, ML, and MS. So this statement is called Pauli exclusion principle. This statement is called Pauli exclusion principle. So in a given atom, no two electrons can have the same set of 4 quantum numbers. That is N, L, MS, and ML and MS. Then, since only 2 values of MS are allowed, an orbital can only hold 2 electrons, and they must have 2 opposite spins. So we know that an orbital can only hold a maximum of 2 electrons. So these electrons in an orbital will have 2 opposite spins. So one up, the one pointing up, the other one pointing down. So that is what it means. Since an electron with the n with the same let's say with n equal to 2 or n equal to 1, will have the same values of n, the same values of L, the same values of ML, but different values of MS, because MS will have 2 opposite spins. 2 opposite spins. So this now qualifies for the Pauli exclusion principle, which says that no 2 electrons can have the same set of 4 quantum numbers. Okay, so this principle have important consequences as we use the atomic model for the electron arrangement. So we use this principle to write also the electron configuration of atoms. So now we can look at the Aufbau principle and the periodic table. We want to see how the electrons are arranged. arranged the Aufbau principle. The Aufbau principle and the periodic table. So as protons are added one by one to the nucleus to build up the elements, to build up the elements, electrons are similarly added to these hydrogen-like orbitals, This is called Aufbau principle. Aufbau principle. So we use this principle to write the electron configuration of atoms. We are going to see how the electron configuration is comes about. So we shall use this principle. For example, hydrogen only has one electron. We'll start with the hydrogen, which has one electron. So we are going to write the configuration for hydrogen. So in this case, the hydrogen configuration will be written, since it only has one electron, so this one electron will fill up the s orbital. So this is the electron configuration for hydrogen, 1s1. So we can also show this using the orbital diagram. So in the orbital diagram, we have 1s, then there's 2s, then we have 2p. So this one, we have these orbitals. Then the p orbital, the p has three orbitals. We have px, py, and pz. So in this case, the electron in the hydrogen atom only occupies the s orbital with a spin pointing up. So the 2s, the 2p are vacant. Then the next element is helium, which has 2 electrons. So helium is the next element, which has 2 electrons. So how are we going to write the electron configuration for helium? So with the helium, we know it has 2. So the electron configuration for helium will be 1s, 1s2, 1s2. So using the orbital diagram, so we have the spin up and there's another one electron pointing up, following the Pauli exclusion principle. So since two electrons with the opposite, so two electrons with the opposite spin can occupy an orbital according to the Pauli exclusion principle. Okay, so this is our 1s, then 2s, then 2p. Then lithium, we can go to lithium. Lithium has 3 electrons. So we have the electron configuration for lithium since it has 3. So in this case, the 1s is already filled up. So for lithium, it will be 1s2. Then the next level will be 2s. Next orbital, that is the 2s. So it will be 2s1, 2s1, 1s2, 2s1. So in terms of the orbital diagram, the 1s is filled up already. We'll have the 1s, then 2s like that. 1s, then 2s, then 2p. Then the next element is beryllium. Beryllium. So we can go to Be, beryllium. Be. So beryllium has 4 electrons. So the electron configuration 1s2, then 2s2, 2s2, as you can see. So it means this 2s is now filled up. This is the 1s, then 2s is filled up. Then we have the 2p, 2s, 1s. So that is the electron configuration for beryllium. Then the next element is boron. Boron, which has 5 electrons. Boron. So we have the boron with the 5 electrons. So the electron configuration for boron will be 1s2, then 2s2. Since the 2s is filled up, the electron now will have to occupy the 2p, orbital. So the electron configuration for boron will be that. So now in terms of the orbital diagram, we have the 1s, which is filled up, then 2s is filled up, then we have 2p. So 2p, the p orbital, there are three p orbitals, and these 3 orbitals are the 2p orbitals have the same energy. They are degenerate. So meaning that they have the same energy. So the electron can occupy any of the 3. So it doesn't matter if it starts here. They are the same. They have the same energy. So suppose the electron occupies this orbital. So we know that all the three 2p orbitals are the same. So this is the
the electron configuration for boron. Then the next for the next one, so this is the n equal to 1, n equal to 1, then n equal to 2. So the third electron will occupy the n equal to 2. Then the next is carbon, which has 6. So in this case, carbon will be 1s2, then 2s2, then 2p2. So in this case, the other electron will fill up the next orbital, which will be written like this. So this is the 1s, which is filled up, 2s, then 2p, like that. 1s, 2s, 2p. Then from carbon, we go to the next element, which has 7. So the element which has 7, that will be now we go to nitrogen. So the electron configuration for nitrogen will be 1s2, then 2s2, then 2p3. So it means now the other orbital is filled up for in the 2p orbital. So this is the 2s, then the 2p. So the 2p orbital will look like that. 1s, this is 1s, then 2s, then 2p. Then from nitrogen, we'll go to oxygen. We'll go to oxygen. So oxygen has 8. So in this case now, oxygen will have 1s2, 2s2, and 2p4. So in this case now, again, the electron will start filling up one by one. Then from oxygen, we'll go to fluorine. Fluorine has 9 electrons. So the electron configuration for fluorine with 9 electrons will look like 1s2, then 2s2, then 2p5. The orbital diagram for fluorine will be, we have the orbital diagram. So these are filled up. The 1s, 2s are already filled up. So this one, so the other electron will go there. In the 2p orbital. Then the next will be neon. So neon has 10. So for neon, it will be 1s2, then 2s2, then 2p6. Then we have the orbital diagram for neon. So we have the 1s, 2s, then this is the 2p orbital. So we can see now that the 2p orbital is filled up. So the next so this means that this atom is stable. There are no unpaired electrons. All the electrons are paired. So it has reached its completely filled up. So the next is sodium with 11. So meaning that from 2p from 2p now, the electron has to go to the n equal to 3. That will be the 3s, the 3s orbital. So for sodium now with 11, it will be 1s2, then 2s2, then 2p6, then 3s1, 3s1. So meaning that we simply add another orbital for the 3s. So now, as you can see, the 1s2, 2s2, 2p6, these are called the core electrons, whereas the 3s, that is the valency, electrons, the inner electrons are called the core electrons. So to avoid writing the inner electrons, or the core electrons, we can use a shorthand notation. So instead of writing 1s2, 2s2, 2p6, we can simply write the electron configuration for sodium as neon core, then 3s1. So the moment we write like this, Ne with these square brackets, we mean that we have 1s2, 2s2, and 2p6. That's the meaning. Then the next we'll have magnesium. So magnesium, which follows, so it will be the electron configuration for magnesium will be neon, then 3s2. So we have seen that the 3s is filled up. So we continue going in that way. Then we can also look at potassium with 19. So we see that the potassium has 19 electrons. So the electron configuration for potassium will be, if I write it in the normal way, 1s2, then 2s2, then 2p6, then we have the 3s2, then 3p6, and the 4s1. So you can see from here up to here we have 18 electrons, and 18 is the argon. So we can write the electron configuration for potassium as argon, then 4s1. Then for calcium will be argon, then 4s2, and so on. So the next element begins with the scandium. A series of 10 elements through zinc, called the transition metals. So we can also look at electron configuration for transition metals. For scandium, Sc, we'll have the electron configuration is argon, then 4s, 4s2, then 3d1. So from 4s we go to 3d. Then for titanium, the electron configuration will be argon, then 4s, 4s2, then 3d2. Vanadium, argon, then 4s2, 3d3. Then we can look at the electron configuration for chromium, Cr. For chromium, the expected configuration for chromium is argon, 4s, 4s2, then 3d4. So this is the expected configuration for chromium. However, the observed configuration for chromium observed configuration for chromium is argon 4s1, then 3d5. So D can carry a maximum of 10 electrons. Then for for copper also has the expected copper. The expected configuration for copper is argon 4s 4s2 and 3d9. So the observed configuration for copper is argon, then 4s1, then this other electron goes to the 3d10. So the 3d is filled up, then the 4s is half filled. Then for zinc, the electron configuration for zinc, that is argon 4s2, then 3d10 and so on. So there are a lot of elements. So these are some of the examples. So we need to follow the energy levels to fill up with these energy levels. Last time we looked at the first 4 levels of hydrogen atom. So we know how the energy levels are